this G is simply an extension of F. It's not necessarily defined on whole F, etc.
थोड़ा बड़ा भी सकते हैं.
बड़ा भी हो सकता है. ठीक है. But we are saying that we can find बड़ा करते करते we can reach to
Maximal.
we can reach to the maximum. That's what the Zorn's lemma is telling us. And hence, E would not be empty because F has at least an extension, which is itself.
Itself.
Let's do this step 1. E is non-empty because at least F belongs to E. Okay? So as we want to apply the Zorn's lemma, okay, we need to define an order. So what do you think, what should be the order? What must be the order that must be defined actually? So in other words, we want to compare the extensions actually. Okay, this one is a bigger extension and this one is a smaller extension somehow of F.
Domain should be
Domains.
So we're going to see basically. So we're going to make sure that, okay, that they are extensions of F and their domains has a relationship actually. So obviously the natural candidate for this extension is going to be this. So for G and H in E, define an order, okay,
Partial order.
denoted by less than or equal to. But this less than or equal to is not less than or equal to. So define order, okay, by that G is less than or equal to F if and only if, no, G is less than or equal to H
domain of G is contained in domain of
if and only if domain of
G
is contained in domain of X.
okay, so the domain of G is contained in domain of H, okay, and making sure that, okay, so it's like this G and F, since they both are from E, they are extending F. But we need to also make sure that G is an extension of G actually. H is the extension of G. Okay. So you have an extension of an extension of an extension. It's something ultimately. Okay. And so what I need to write? So I need to write that H of X and G of X must agree
Or domain of G.
for all X in
Domain of G.
domain of G actually. Okay. So this is what essentially you have to do. Partial order is pretty trivial. You have to think for yourself because we know that this is a partial order essentially. That's the key thing. So you have this containment actually. Okay. So we know that it's reflective, it's antisymmetric, it's transitive. So there's nothing difficult in proving that this is a partial order. But you must verify. Okay. You must write a proof, a very clear proof of it. So what you need to verify is that this E with this order is a cosine. Is a cosine. Okay? It's a cosine. So verify. What we need to do next is to take a chain, okay, and show that it has an upper bound. So if you take some number of extensions of F, which can be compared with this order, okay, because chain means a totally ordered subset actually. In other words, something in which you can compare all possible two elements actually. Okay, so let C be a chain, and we want to prove that that chain has an upper bound. Not that F tilde necessarily, because chain is just a subset of E actually. Okay. But it's not necessary that the whole E must be a chain. Okay. Well, E is not necessarily a chain. Okay. So let C be a chain in E. I mean, if you want to treat it, you can treat it as like the way I wrote that, okay, F1 is less than or equal to F2, F2 is less than or equal to F3, and so on and so forth with respect to this one. Okay. If this is the case, I would like to say that, okay, what would be the function actually, okay? What would be, so how can I construct an upper bound for this actually? Give me an idea, think about it.
H of x belongs to follow on x.
If there is an upper bound for this chain, how does that upper bound should look like actually?
So it should be the
Domain.
domain should be union of all domains.
Yes. It must be domain of union of all domains, and it must be extending the every single element in the E actually. Okay? So it's pretty much natural actually. Think about it. Is it reminding of you of something actually when you are proving what you call least upper bound property? Okay, through cuts. And you have a set and you try to construct it. What do you call an upper bound for it? You just took simply union and check that worked. So it's pretty much something similar. Okay. All right. So it's a sign that in words of Banach that if you can see the analogies between proofs, we are improving. We are improving actually. So we must improve. Exactly. Okay, so let me define a function g hat, okay, by that g hat of x is equal to g of x for all x in domain of G. In other words, that G hat is extending every single element in C. So it's an extension of every single element. So that's what it says, that you take any G, then G hat is extending it. Okay, it's like they both agree on the domain of the G. And define what must be the domain of G? What would be the domain of G hat? So the domain of G hat must be the union of all domains of the G's which are in the C actually. So it's like it's the union, okay, of G's in C
Domain of G.
and their domains actually. Okay. Obviously, there would be a little bit, loophole, something that we need to verify, is that, is this a subspace actually? It's going to be something which you need to make sure that is true actually. So would that be a subspace? Here's a question for you, sir. So in other words, is G hat a linear functional? Okay? So is G hat a linear functional? They are extensions of a linear functional. So is extension of a linear functional a linear functional? Secondly, is the domain of G hat a subspace? Of X actually. Okay, something left for you to do actually. Pretty simple. Think about it. Okay. your life easier, you may add a word here that these G's are linear extensions of f. Okay? Now maybe you can see that. Linear functions of f. G is linear extension of f. This G hat must be also. So this is something for you to verify. Now here is a fundamental question now. You have to find an element in C which is kind of an upper bound for the whole chain. So we need to make sure that the G hat that we have defined is also an element in C. Okay. It's an element in C. Would that be an element in C? Imagine that we proved these both things. Okay. And it's going to Alright, so what I need to prove next is that why G is an upper bound for C. Why G hat is an upper bound for C. Another thing that I would suggest to you that while proving that this is a subspace, this chain structure has a role actually, so don't ignore it. You have to keep in head that C is a chain actually. So the chain is going to play a role. Okay? So keep the context in head actually when you want to prove this small result. Okay, so we have a linear functional, we have a linear functional which is kind of extending every single element in C, and its domain is domain of G hat, okay, and so on and so on. And I can say actually, I can conclude it here that hence, if this is true, then G hat is upper bound for C. Agreed? Because what would be the meaning of upper bound? That every single element can be compared with this G hat actually, and by definition this is true. Okay. G hat is extending every single element in the factory. Okay? If this is the case, we took chain, we defined an element, we defined a function G hat, we saw that, we saw that it's an upper bound for this whole C, so we are in the business of Zorn's lemma. So Zorn's lemma is telling us, is going to tell us that there is a, so by Zorn's lemma, okay, there exists an f hat in, what do we call, E, okay, such that f is less than or equal to f hat for all f in E actually, so it's kind of an extension, okay, and obviously
सर इसको G कर दीजिए.
Huh?
Replace F with G. F is fixed over here.
Okay, G. So it's kind of a maximum element. And since this f hat is in E, so obviously f hat of x must be less than or equal to p of x for all x in what? Domain of G hat.
F hat.
F hat, sorry. Yes. Okay. So it's at this point. So this kind of completes the proof of the first step actually that we did. So now we like to go further. The second step actually, which says that
It is defined on the whole X.
the step 2 is going to be to show that the domain of f hat,
Is X.
f hat or f tilde, we must write tilde because we reserved this symbol tilde is whole accent. Okay? This is what that we would like to show. Did you realize here that, you know, really the Zorn's lemma is kind of a result in which you are not constructing a maximal element essentially. Okay? It just says that it exists.
Making sure.
Okay? Sure that it exists, but we are not constructing it. So in other words, when you just want existence, probably this is a good result actually. But if you have a practical problem, okay, where you not only have to show the existence, but you have to kind of devise an algorithm that how to, you know, construct that particular object, then that's not a good choice actually. Okay? You know, can we get away from the Zorn's lemma? You know, the answer is here. You can read it actually. Okay? So after the proof of this, it talks about it that, okay, how you can we prove this result without using Zorn's lemma? Look for the book actually. Let me not reveal this answer. Okay. So we want to show this. We're going to show it through contradiction. We're going to say that suppose not. Suppose not. Suppose that f is not whole accent. And what I'm going to do, I'm going to construct an element which is bigger than this maximal element in E.
And extend
So it's going to contradict that.
extend to f tilde.
Yes, so it's going to be an extension of f tilde. So in other words, we're going to get a contradiction to the maximality of this f tilde. So that's what we are heading actually. Okay, so if this is not true, then what is true?
Domain of F tilde is subset of X.
Okay, so in other words, there exists
Some
Some-
subset of X.
some maybe, okay, let's call it a y1, okay, in X such that this y1 is not in E. Okay,
Domain.
not domain, sorry.
Yeah, domain of
Domain of F
domain of f tilde.
domain of F tilde. Okay. Tilde.
And not.
Not. कहाँ मैंने वही ठीक है जी. So this must be the case. Now, can you, if this is the case, just think about it. Can you give me a space which is bigger than this domain of F tilde?
Domain of this and union of y.
Okay, so what I can do is that take the union of the subspace generated by y1 and this domain. So it's going to be subspace actually. Okay. So if I take a subspace generated by y1 and this domain of f tilde, which is subspace indeed, okay, then that is going to be a bigger space than domain of f tilde. Okay. Maybe between domain of f tilde and x actually. So what I'm going to do, that on that union, I'm going to define an extension in such a way that that is going to be bigger than this f tilde actually, essentially, and it's going to contradict the maximality. A pretty natural idea. Pretty natural idea. So consider what? Consider y1 as a space that is spanned by domain of f tilde and y1. Okay, so it's like taking all possible linear combinations, okay, from domain of f tilde and y1 actually. Okay, so it's like this linear combination, like in this, okay, so it contains all linear combinations from here and the linear combinations of obviously this and that actually. Maybe the better is to call such kind of statement. Okay. Well, it's not a Buddhist notation actually, because we know that the span is a set actually. Span is a set. Okay.
Set of sets
So the better to write it in words actually. Okay. So let's say that y1 is a subspace, okay, spanned by the union of f tilde and y1. Okay. I'm putting an additional assumption on it, that it must be non-zero. Why? Just think about it. Because if y1 is 0,
It should be in
so it should be in domain of f tilde because it's a subspace.
subspace.
Okay. So if it's not in subspace, then we're going to say that this is something different from 0. Okay. All right. So if I take an x from y1, how does it look like?
Linear combination.
It's not true.
So it's going to be the linear combination of an element from domain and this actually. So x can be written as, okay, what? Some y, okay, which is from domain tilde plus alpha times y1. Y is from domain of f tilde and alpha is scalar. Agree? This is going to be the case. And my claim is that this representation is also going to be unique actually. Okay? This representation is going to be unique as well. Why? Because y1 is non-zero. So I can prove it. I can prove it that imagine, so like to see, so above representation is unique. Unique. Why? Because if you take any other representation, so it's like a y tilde plus, okay, some beta y1 actually. Okay? Then my claim is that these must be same. Why this would be the case? Think about it. So take a difference of both. So you're going to get to 0. It's like a y minus y tilde plus alpha minus beta times y1, and there's 0. Okay? Now, how you can have this whole expression to be 0? So just think about it. y1 is not 0. y1 is not 0. So if y1 is not 0, this whole sum has to be 0. So this term must be 0 and this coefficient must be 0. Think about it. So I'm saying that, the difference of these two guys is 0.
Y1 is
Okay, and y1 is not 0. Imagine that this coefficient is not 0. Then this sum is not 0. Okay? So if you want, this sum to be 0, then this term and the coefficient must be 0, because there is no other way actually. Okay?
Minus 10, 0.
So since
y1 ना है कदे y1 नहीं दोनों हाँ
since y1 is not 0, okay, this implies that y must be same as y tilde and alpha must be same as
Y1 increases.
सर ये दोनों एक्सप्रेशन इक्वल भी तो हो सकते हैं ना माइनस टाइम्स y माइनस वाई टिल्डा प्लस अल्फा माइनस बीटा टाइम्स y1 मतलब एक एक्सप्रेशन के एक दूसरे के माइनस
okay.
पॉसिबिलिटी हो सकती है
So linearly independent.
Yes,
Sir,
the
y1
linear
is not
independence would-
exactly.
would
Y1
not,
is
yes.
another expression.
So since y1 is not 0 and these both must be linearly independent, okay? Because just think about,
Linearly independent.
Because if they are linearly dependent, then y1 can be written as the linear combination of elements from domain of f tilde and hence belong to domain of f tilde. Okay? So
linearly independent.
this representation must be unique. Alright. This representation must be unique. Okay. Now we are in position to define a functional on y1. And I'm going to show that that functional extends f tilde in such a way that it also satisfies this property. And hence that would be the contradiction to the maximality of what do we call f tilde. Okay. So let's define a functional. Define a functional g1 from y1 into r by that whenever g1 is operating on y plus alpha y1. Okay. So why there was an emphasis on showing that like the representation must be unique, because then I can talk about this.
Well-defined thing.
Yes. Okay. So what would be that? So the definition of this, that operate f tilde on y plus alpha times on c. Okay. Where c is some fixed real number. Alright. Okay. So c is real. So it's like c is not depending on this expression. So it's like a fixed number. So I can put a 1/2 here. Something like that. Okay. So verify that G1 is linear. Verify that given is linear. How can I show that G1 extends F tilde?
Domain of F tilde